Okay, so let's look at this tremendously interesting problem, okay, that involves a a block of mass m that is sliding down an inclined plane. It starts from rest and it hits the spring, okay, with a certain speed, and we want to find out what the speed of the block is when it hits the spring. So it has been stated that the block stops momentarily when the spring is compressed by 5.5 centimeters. And we want to know, what the speed is of the block. Right? So that the spring is such that when it is compressed by 2 centimeters, there's a force of 270 newtons that needs to be applied. Okay, so these are the things that have been told to us. So the question is, how are we going to attempt this problem? So let's start by using the the work energy principle. So the work energy principle is that work done on the block equals change in the kinetic energy of the block. Okay. So that's the work energy theorem. So what is the work done on the block? The work done on the block is essentially, if you look at the net force, okay, and we are going to compute the net force from here, from this force diagram. So we consider that the block is displaced by a small amount dx. So the work done the for that little displacement is the net force times dx. So we want to integrate to find the total work. Okay, so we integrate from 0 to L, okay, where L is the maximum displacement of the block. So the question is, what is this F net? So the F net, if you look here, so it comprises two portions. If you look at the force diagram along uh, along the inclined plane, so the downward force due to gravity is mg sine theta. Okay, the upward force that is resists the downwards motion of the block, okay, is kx, and this is the resistance of the spring. So we can write F net. Okay, we can write F net equals mg sine theta minus kx. So this work done becomes integral 0 to L mg sine theta minus kx dx. So we can split this into two different integrals, 0 to L mg sine theta dx minus kx dx between 0 to L. So this becomes mg sine theta times L minus 0 minus half k L square minus 0 square equals mg sine theta times L minus half kl square. So 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 now we want to find out the next portion, that is, what is the change in the kinetic energy of the block. Right. So when the block hits the spring right here, its velocity is v. So the initial kinetic energy equals half mv square, and what's the final kinetic energy of the block? That's 0, because the block is momentarily resting at that particular point. So as a result, we get delta Ke, the change in kinetic energy, is minus half mv square. So we take this expression 1 and expression 2 and equate them. When we do that, we get mg sine theta times L minus half KL squared equals minus half mv square. So let's rewrite this. We get mg sine theta plus half mv square. Well, let me write this a little bit nicer. Half KL squared. So if we see this very carefully, right? So what has happened here is that this really looks like we are equating two different energies, and which is correct. So what happens here is that if we rewrite this expression here, realizing that if the block slides down by length h, it has fallen by height h, and L sine theta is just h. We can rewrite this as mgh plus half mv square equals half kl square. So if we see that the expression on the left is just the initial energy of the block, because it has a potential energy of mgh. Okay, when it hits the spring right here, right, and its velocity is v, so its kinetic energy is half mv square. So the total energy of the block to begin with is mgh plus half mv square. Now the potential energy of the spring to begin with is 0, but now what happens after the block comes to rest here? So its potential energy is 0 because this is our reference point, and since the block is resting against the spring, its kinetic energy is also 0. What we have got instead is the potential energy of the spring. So the total energy of the block has been converted to the total energy of the spring. So this is just a law of conservation of energy. That's all it is. So we can do this problem two ways. We can use the conservation of energy, or we can use the work energy theorem. We could use either of these. But when done properly and correctly, this should give us the same answer. So let's rewrite this expression. Here, if we rewrite this expression, we get k divided by m times L squared minus 2 GL sine theta, and we take the square root of that. Now the question is, what is K? K is 270 newtons divided by 0.02 meters. L is 5.5 divided by 100 meters. Okay. Theta equals 30 degrees, and m equals 12 kilos. So we substitute that, we get 270 divided by 0.02 times 1 over 12, that is the mass in kilograms, 5.5 divided by 100 squared, minus 2, g is 9.8 meters per second square, length is 5.5 divided by 100, and sine theta is half, because theta is 30 degrees. So if we do that, we get approximately 3.4 minus 539. Take the square root of that. You get approximately 1.7 meters per second. Okay. So what we have seen here is that we could use this method, that's the conservation of energy, or we could use the work energy relationship. Either of these, okay, when used properly and correctly, will give us the same answer. Okay, so both these approaches are equivalent. So this problem illustrates not only how inclined plane can be solved, problems can be solved, but also how different approaches can be used to solve the same problem. Okay, and I hope this will give you an insight into solving such problems in the future. Thank you.